Doctoral dissertation on the size of molecules, April 1905. Einstein had written a paper that would revolutionize science, but he had not yet been able to earn a doctorate. He realized that he needed a safe topic, not a radical one like quanta or relativity, so he chose the second paper he was working on, titled A New Determination of Molecular Dimensions, which he completed on April 30th and submitted to the University of Zurich in July. Perhaps out of caution and deference to the conservative approach of his advisor Alfred Kleiner, he generally avoided the innovative statistical physics featured in his previous papers and in his Brownian motion paper completed 11 days later, and relied instead mainly on classical hydrodynamics. Yet he was still able to explore how the behavior of countless tiny particles, atoms, molecules, are reflected in observable phenomena, and conversely, how observable phenomena can tell us about the nature of those tiny unseen particles. Almost a century earlier, the Italian scientist Amedeo Avogadro, 1776 to 1856, had developed the hypothesis, correct as it turned out, that equal volumes of any gas, when measured at the same temperature and pressure, will have the same number of molecules. That led to a difficult quest, figuring out just how many this was. The volume usually chosen is that occupied by a mole of the gas, its molecular weight in grams, which is 22.4 liters at standard temperature and pressure. The number of molecules under such conditions later became known as Avogadro's number. Determining it precisely was, and still is, rather difficult. A current estimate is approximately 6.02214 times 10 to the 23rd. This is a big number. That many unpopped popcorn kernels, when spread across the United States, would cover the country 9 miles deep. Most previous measurements of molecules had been done by studying gases. But as Einstein noted in the first sentence of his paper, the physical phenomena observed in liquids have thus far not served for the determination of molecular sizes. In this dissertation, after a few math and data corrections were later made, Einstein was the first person able to get a respectable result using liquids. His method involved making use of data about viscosity, which is how much resistance a liquid offers to an object that tries to move through it. Tar and molasses, for example, are highly viscous. If you dissolve sugar in water, the solution's viscosity increases as it gets more syrupy. Einstein envisioned the sugar molecules gradually diffusing their way through the smaller water molecules. He was able to come up with two equations, each containing the two unknown variables, the size of the sugar molecules and the number of them in the water, that he was trying to determine. Einstein later said, perhaps half-jokingly, that when he submitted his thesis, Professor Kleiner rejected it for being too short, so he added one more sentence and it was promptly accepted. There is no documentary evidence for this. Either way, his thesis actually became one of his most cited and practically useful papers, with applications in such diverse fields as cement mixing, dairy production, and aerosol products. And even though it did not help him get an academic job, it did make it possible for him to become known, finally, as Dr. Einstein. Brownian motion. May 1905. 11 days after finishing his dissertation, Einstein produced another paper exploring evidence of things unseen. As he had been doing since 1901, he relied on statistical analysis of the random actions of invisible particles to show how they were reflected in the visible world. In doing so, Einstein explained a phenomenon known as Brownian motion that had been puzzling scientists for almost 80 years. Why small particles suspended in a liquid such as water are observed to jiggle around. And as a byproduct, he pretty much settled once and for all that atoms and molecules actually existed as physical objects. Brownian motion was named after the Scottish botanist Robert Brown, who in 1828 had published detailed observations about how minuscule pollen particles suspended in water can be seen to wiggle and wander when examined under a strong microscope. The study was replicated with other particles, including filings from the Sphinx, and a variety of explanations was offered. Perhaps it had something to do with tiny water currents or the effect of light, but none of these theories proved plausible. With the rise in the 1870s of the kinetic theory, which used the random motions of molecules to explain things like the behavior of gases, some tried to use it to explain Brownian motion. But because the suspended particles were 10,000 times larger than a water molecule, it seemed that a molecule would not have the power to budge the particle, any more than a baseball could budge an object that was a half-mile in diameter. Einstein showed that even though one collision could not budge a particle, the effect of millions of random collisions per second could explain the jig observed by Brown. In this paper, he announced in his first sentence, it will be shown that, according to the molecular kinetic theory of heat, bodies of a microscopically visible size suspended in liquids must, as a result of thermal molecular motions, perform motions of such magnitudes that they can be easily observed with a microscope. Einstein realized that a bump from a single water molecule would not cause a suspended pollen particle to move enough to be visible. However, at any given moment, the particle was being hit from all sides by thousands of molecules. There would be some moments when a lot more bumps happened to hit one particular side of the particle. Then, in another moment, a different side might get the heaviest barrage. The result would be random little lurches that would result in what is known as a random walk. The best way for us to envision this is to imagine a drunk who starts at a lamppost and lurches one step in a random direction every second. After two such lurches, he may have gone back and forth to return to the lamp, or he may be 2 steps away in the same direction, or he may be 1 step west and 1 step northeast. A little mathematical plotting and charting reveals an interesting thing about such a random walk. Statistically, the drunk's distance from the lamp will be proportional to the square root of the number of seconds that have elapsed. Einstein wanted concrete predictions that could be tested, so he used both his theoretical knowledge and experimental data about viscosity and diffusion rates to come up with precise predictions showing the distance a particle should move depending on its size and the temperature of the liquid. For example, he predicted in the case of a particle with a diameter of 1/1000th of a millimeter in water at 17 degrees centigrade, the mean displacement in 1 minute would be about 6 microns. Here was something that could actually be tested, and with great consequence. If the motion discussed here can be observed, he wrote, then classical thermodynamics can no longer be viewed as strictly valid. Better at theorizing than at conducting experiments, Einstein ended his paper with a charming exhortation. Let us hope that a researcher will soon succeed in solving the problem presented here, which is so important for the theory of heat. Within months, a German experimenter named Henry Seidentopf, using a powerful microscope, confirmed Einstein's predictions. For all practical purposes, the physical reality of atoms and molecules was now conclusively proven. At the time, atoms and molecules were still far from being regarded as real, the theoretical physicist Max Born later recalled. I think that these investigations of Einstein have done more than any other work to convince physicists of the reality of atoms and molecules. A strength of Einstein's mind was that it could juggle a variety of ideas simultaneously. Even as he was pondering dancing particles in a liquid, he had been wrestling with a different theory that involved moving bodies and the speed of light. A day or so after sending in his Brownian motion paper, he was talking to his friend Michele Besso when a new brainstorm struck. It would produce, as he wrote Habicht in his famous letter of that month, a modification of the theory of space and time. Special Relativity, 1905. The background. Relativity is a simple concept. It asserts that the fundamental laws of physics are the same, whatever your state of motion. For the special case of observers moving at a constant velocity, this concept is pretty easy to accept. Imagine a man in an armchair at home and a woman in an airplane gliding very smoothly above. Each can pour a cup of coffee, bounce a ball, shine a flashlight, or heat a muffin in a microwave, and have the same laws of physics apply. In fact, there is no way to determine which of them is in motion and which is at rest. The man in the armchair could consider himself at rest and the plane in motion, and the woman in the plane could consider herself at rest and the earth as gliding past. there is no experiment that can prove who is right. Indeed, there is no absolute right. All that can be said is that each is moving relative to the other. The special theory of relativity that Einstein developed in 1905 applies only to this special case, hence the name, a situation in which the observers are moving at a constant velocity relative to one another, uniformly in a straight line at a steady speed, referred to as an inertial reference system. The story of relativity best begins in 1632, when Galileo articulated the principle that the laws of motion and mechanics, the laws of electromagnetism had not yet been discovered, were the same in all constant velocity reference frames. In his dialogue concerning the two chief world systems, Galileo wanted to defend Copernicus's idea that the Earth does not rest motionless at the center of the universe, with everything else revolving around it. Skeptics contended that if the Earth was moving, as Copernicus said, we'd feel it. Galileo refuted this with a brilliantly clear thought experiment about being inside the cabin of a smoothly sailing ship. Shut yourself up with some friend in the main cabin below decks on some large ship, and have with you there some flies, butterflies, and other small flying animals. Have a large bowl of water with some fish in it. Hang up a bottle that empties drop by drop into a wide vessel beneath it. With the ship standing still, observe how carefully the little animals fly with equal speed to all sides of the cabin. The fish swim indifferently in all directions. The drops fall into the vessel beneath. And in throwing something to your friend, you need to throw it no more strongly in one direction than another, the distances being equal. Jumping with your feet together, you pass equal spaces in every direction. When you have observed all these things carefully, have the ship proceed with any speed you like, so long as the motion is uniform and not fluctuating this way and that. You will discover not the least change in all the effects named, nor could you tell from any of them whether the ship was moving or standing still. There is no better description of relativity, or at least of how that principle applies to systems that are moving at a constant velocity relative to each other. Sound waves and water waves are easily explained by classical mechanics. They are simply a traveling disturbance in some medium. That is why sound cannot travel through a vacuum. But it can travel through such things as air or water or metal. For example, sound waves move through room temperature air as a vibrating disturbance that compresses and rarefies the air at about 770 miles per hour. Deep inside Galileo's ship, sound and water waves behave as they do on land, because the air in the chamber and the water in the bowls are moving at the same velocity as the passengers. But now imagine that you go up on deck and look at the waves out in the ocean, or that you measure the speed of the sound waves from the horn of another boat. The speed at which these waves come toward you depends on your motion relative to the medium, the water or air, propagating them. In other words, the speed at which an ocean wave reaches you will depend on how fast you are moving through the water toward or away from the source of the wave. The speed of a sound wave relative to you will likewise depend on your motion relative to the air that's propagating the sound wave. Those relative speeds add up. Imagine that you are standing in the ocean as the waves come toward you at 10 miles per hour. If you jump on a jet ski and head directly into the waves at 40 miles per hour, you will see them moving toward you and zipping past you at a speed, relative to you, of 50 miles per hour. Likewise, imagine that sound waves are coming at you from a distant boat horn, rippling through the still air at 770 miles per hour toward the shore. If you jump on your jet ski and head toward the horn at 40 miles per hour, the sound waves will be moving toward you and zipping past you at a speed, relative to you, of 810 miles per hour. All of this led to a question that Einstein had been pondering since age 16, when he imagined riding alongside a light beam. Does light behave the same way? Newton had conceived of light as primarily a stream of emitted particles. But by Einstein's day, most scientists accepted the rival theory, propounded by Newton's contemporary Christian Huygens, that light should be considered a wave. A wide variety of experiments had confirmed the wave theory by the late 19th century. For example, Thomas Young did a famous experiment now replicated by high school students, showing how light passing through two slits produces an interference pattern that resembles that of water waves going through two slits. In each case, the crests and troughs of the waves emanating from each slit reinforce each other in some places and cancel each other out in some places. Robert Clerk Maxwell helped to enshrine this wave theory when he successfully conjectured a connection between light, electricity, and magnetism. He came up with equations that described the behavior of electric and magnetic fields, and when they were combined, they predicted electromagnetic waves. Maxwell found that these electromagnetic waves had to travel at a certain speed, approximately 186,000 miles per second. That was the speed that scientists had already measured for light, and it was obviously not a mere coincidence. It became clear that light was the visible manifestation of a whole spectrum of electromagnetic waves. This includes what we now call AM radio signals, with a wavelength of 300 yards, FM radio signals, 3 yards, and microwaves, 3 inches. As the wavelengths get shorter and the frequency of the wave cycles thus increases, they produce the spectrum of visible light, ranging from red, 25 millionths of an inch, to violet, 14 millionths of an inch. Even shorter wavelengths produce ultraviolet rays, X-rays, and gamma rays. When we speak of light and the speed of light, we mean all electromagnetic waves, not just the ones that are visible to our eyes. That raised some big questions. What was the medium that was propagating these waves? And their speed of 186,000 miles per second was a speed relative to what? The answer, it seemed, was that light waves are a disturbance of an unseen medium, which was called the ether, and that their speed is relative to this ether. In other words, the ether was for light waves something akin to what air was for sound waves. It appeared beyond question that light must be interpreted as a vibratory process in an elastic, inert medium filling up universal space, Einstein later noted.